In this video, presented by the Material Science and Engineering Department of Arizona State University, we will be discussing the process of testing the mechanical properties of metals using a tensile tester.
Tensile tests are a simple and well-established method of learning about the mechanical properties of your material. This is useful for designing structures and determining the least amount of material you can use to safely design a building, machine, or even a space shuttle. It is critically important in the aerospace industry where safety margins are kept intentionally small in order to reduce fuel costs.
The goal of this lab is we'll be observing the mechanical properties of metals and alloys. We'll be using a 1045 and 1018 steel. And we'll be observing the nature of the tensile deformation. We'll also be using a computer software that will collect data. And from this data, we'll generate a stress and strain curve and also calculate the true stress and true strain curve.
The tensile tester we will be using is an Instron 4411 courtesy of Dr. Dallas Kingsbury. The Instron 4411 tensile tester has a maximum capacity of 5,000 newtons and is ideal for testing the tensile strength of metals. The sample being used for our test is a 1045 steel sample that has been cut into this dog bone shape. This diagram was provided in our lab manual. A small notch is made in the middle of the sample to ensure that it shears in the exact center. Calipers are used to measure the gauge length prior to and after the test, as well as the diameter. The sample is loaded into the tensile tester like so. The sample is extended at a rate of 0.4 inches per minute, and data is collected at a rate of 5 points per second. The load is applied to failure. As the load is applied, data relating load to elongation is automatically recorded. Note that strain equals elongation over gauge length. Here is a close-up of the extensometer you can see Dr. Kingsbury setting up in the last clip. The extensometer is used to measure the change in length of the dog bone sample here, and is very useful for creating stress-strain graphs. Also in this clip we can see the point of failure. After the sample is broken, remove it from the jaws of the machine and measure the final elongation by placing the two pieces back together and measuring the distance between the gauge marks.
The load and elongation data that was obtained can be seen in this graph. It follows a logarithmic pattern. The load elongation data can be converted to stress and strain values using their respective equations. These values are plotted using the strain on the x-axis and the stress on the y-axis. Many different properties can be determined from the stress-strain curve. Here we see the Young's modulus, yield strength, ultimate tensile strength, percent elongation, reduction in area, and toughness for a sample of 1018 steel. A sample of 1045 steel was also tested. This graph shows the load elongation data for this particular sample. As mentioned earlier, the stress and strain values can be calculated from the raw data. This graph shows the stress-strain curve for 1045 steel. The various materials properties were found from the graph and are listed here.
This table summarizes the mechanical properties of the samples. As you can see, the 1045 steel is stronger than the 1018 sample, but is also much more brittle. This brittle behavior is because the 1045 steel has more carbon than the 1018 steel. The carbon atoms are diffused throughout the crystal structure in the interstitial locations of the unit cell. These carbon atoms interact with the iron to form a ceramic material called cementite, which is very strong, but much more brittle than the bulk iron. Additionally, the size of the carbon atoms relative to the iron is perfect for introducing a slight amount of strain in the crystal structure, which acts as a barrier to dislocation movement. Here we display some of the equations for converting the output data from a tensile test to a universal format that can be communicated in a standardized form, without your audience having to know the dimensions of your samples. Notice that an engineering stress-strain curve starts going back down after a while, whereas the true stress-strain curve always has a positive slope. This decreases because the sample undergoes necking, or a localized decrease in the cross-sectional area which is not taken into account because engineering stress-strain curves are based on the initial cross-section area of the sample. A true stress-strain curve is based on the instantaneous cross-section area, and because the sample is undergoing cold working throughout the test, the stress required to strain the material by a specific amount increases throughout the duration of the test. When performing tensile tests, we use dog bone samples to improve the accuracy of the measurement. Due to the smaller cross-sectional area in the center, the sample is likely to begin necking and fail in this region. If the sample had the same cross-sectional area throughout, the sample would fail where it was attached to the tensile tester because there are extra loads applied at these locations. The American Society for Testing and Materials International provides standards for tensile tests. There are a variety of factors that will impact the results you receive during your test. Some of these are material dependent, while others are dependent on the testing procedure itself. For instance, if a sample has been cold worked before the test, it will have a greater Young's modulus but decreased ductility to one that has just been annealed. Additionally, if the strain rate is decreased, the material will have a decreased Young's modulus but improved ductility. The exact mechanism for this behavior is material dependent, but one common reason is because the atoms have more time to rearrange themselves. This is why you can slowly pull silly putty and it will stretch an enormous amount before it breaks. However, if you pull on it quickly, it will tear immediately. This is important to consider when designing components. For instance, if a load is applied over a large amount of time, the part may be able to absorb the energy, but if it undergoes a sudden collision, it may shatter instead. In conclusion, tensile tests are an extremely important technique to have in your engineering toolkit. They're a reliable method for determining the mechanical properties of a material, either when testing a batch to ensure quality control or after developing a novel material that has never been seen before. It is important that the test is standardized and the testing conditions are recorded in order for others to confirm your results. We'd like to thank you for your time and hope you've learned something today.